I've recently begun my 70th deep dive into the Windows API, and it's been interesting. It doesn't just involve reading, rereading, and triple reading the MSDN docs, but most of it is just that. It also means understanding how Windows itself organizes its functionality. It means enumerating functions, data types, classes, and all of that kind of stuff too. One of the cornerstones of the Windows operating system is the humble process. Processes are running programs that have their own private memory space, stack, and a single thread of execution. Now, we're going to get into threads later, I'm sure, and oh boy, is multi-threading going to be a fun topic. But for right now, let's assume we're dealing with single-threaded programs, because those functionally mean that a thread is the same as a process. A single-threaded process only has one thread, obviously. That means one memory space and one thread of execution. This will matter later on, but for now, let's assume that a thread and a process can be understood as the same thing. Now, what do I mean by one singular memory space? Well, this means that a process that has a global or a local variable foo can't be accessed by the function of another process accidentally or easily. I can't spin up a process that has a local variable secret key and then easily access that secret key variable from another process. This is, as you can imagine, fairly important for security purposes. You don't want an untrusted program being able to read variables like passwords and private information from all other processes, at least very easily. So basically everything you do on the Windows operating system is done through a process. Double-click on an icon, open a link, read or write data, just about everything functions through processes. When you spin up your browser to go to my YouTube channel and hit subscribe to get updates on my latest video, you opening the browser spins up at least one process, with its own running thread and its own memory space. How then can we look at those processes? Well, it's actually incredibly easy with your favorite OS shortcut, Control-Alt-Delete. This opens the Task Manager, which notably uses the term task for no functional reason since tasks aren't a thing in the Windows OS terminology. What this really is the Process Manager. You can see what processes are running, how much RAM they're chewing up, what threads they create, etc. For a bit more information, we can use the sysinternals Process Explorer to see more detailed information about processes and their threads in memory. But what if we want to do it using code? This is super useful for writing malware, debugging C++ programs, or just kind of poking around at stuff for research. As you probably guessed, there's an API call for that. Technically, there are 3 that we're going to be talking about in this video, so let's just dive right into it. Alright, so we've got Visual Studio open, and all I've done is created a main.cpp file. We're going to do a couple of imports before we jump right into it, just to kind of save time for later. So we're going to include windows.h. That is all things Windows API. Most of them are within windows.h. We are going to include iostream because that's going to give us access to printf. We're going to include the process API.h, and we are going to include the tchar.h file. That's going to give us access to some printing functions that are actually going to allow us to print tchars, which are a different kind of string functionally. Now let's create our main function. We're not going to worry about any input variables here, and we are going to printf enumerating processes, because that's going to be what we're doing in this video. All right, and we need a semicolon, and we are going to return 0. Now let's run this, just make sure that it actually compiles correctly, and we get enumerating processes. So everything is compiling correctly. Now, a couple of things that we're going to do. We're going to actually start with an API call, and this API call is going to be EnumProcesses or EnumProcesses. First, we have to set up a couple of variables to hold information that EnumProcesses is actually going to output into. So we're going to create a dword array called prox arr of size 1024 just by default, and we're going to say needed is going to be the name of the next dword. Now we're going to actually call EnumProcesses. We're going to store the output in prox EnumProcesses, and we're going to open up the MSDN article on this function. By default, just always go straight to the MSDN article and read about it before you actually try to call it. So if we go to EnumProcesses here, we're going to see the way that we call it, and we're going to see what it actually does. It's going to return the process identifier for each process object in the system. Now, as I've kind of explained already, processes are the basic building block of running any code on Windows. Each individual process is going to have its own memory space, and it's going to have a bunch of other associated information, some of which we're going to actually deal with in this video. One of the most important pieces of information in this context is the process identifier, the PID. The process identifier, all it really is it's a number that corresponds to each individual process. You can actually see the PIDs if you open up something like Process Explorer from sysinternals. So let's open up Process Explorer and we can look at all of the PIDs here. So if we order by PID, we can see that there are hundreds and thousands and tons of PIDs here, all of them corresponding to individual processes running on our system. So we've got one for Slack, we've got one for our dev environment within Visual Studio, we've got two for Discord. Like I said, open up a Discord server, feel free to jump in if you want to kind of join in on all of the research fun. And each one of these processes is going to have its own unique PID. That PID is going to become very important in just a second, as is this lower pane window right here. But we will deal with that when we get to it. So let's go back to this MSDN article. We've got the out. This is an output of the function. So we're going to pass it in a pointer to a variable that it will then output data into. So this LPID process variable right here is just going to be a holder for the array of PIDs. This right here is going to be the size of that array that we pass in, and this other output variable is going to be the size that the operating system says we actually need to devote to this array of process identifiers. So it's going to basically have two different outputs and one input, but all three of those things are actually going to be inputted into the function. This is a fairly standard way to call functions within the Windows API from what I've found. They really like these kind of void-esque type functions. Obviously, this is going to return a Boolean, whether or not it passed or failed, but it's technically a void function. Basically, all it's doing is it's taking a pointer as an input that it is going to use to then store the output of that function, which is fairly common within void functions. We're actually going to write a void function in this video that is going to do functionally the same thing. So let's go back to our code. So we've got EnumProcesses. We're going to hand it the procs array, which by default is passed by reference. So it's by default, passed the actual location of that array whenever you call this function. Then we're going to pass in the size of procs ARR. Instead of just writing 1024, I'm going to do size of procs ARR so we can kind of do it a little bit more dynamically. And then we're going to pass in the location of needed. And that's really it. So let's go ahead and kind of do some looking at this function. I'm going to create two different prints. We're going to do printf before and predictably printf after. And all I'm going to be using these for is as placeholders for our breakpoints. So I'll put a breakpoint here and a breakpoint here, and we're going to run this in debugging mode. So when we run this, we can actually view the values that are held within all of these variables. So we see that needed holds some nonsense value, procs holds some nonsense value, and procs array also holds some nonsense values. Now, the keen-eyed of you will look at this and say, wait, all of these individual items within procs array are the exact same value, and they're actually the exact same value as is stored in needed. Why is that the case? Well, this is actually a value that your debugger is going to store to basically say this memory region is uninitialized. So if we actually go into hex mode, which we can do right here, hexadecimal display at 0xCCCCCC. So all C's is basically the debugger's way of saying, hey, this memory region has not been initialized. There shouldn't be anything important in it. We shouldn't be reading from it. We shouldn't be messing with it. So let's switch back out of hexadecimal display. And that's basically just the debugger's way of saying this is kind of dangerous, memory region. Don't just read from this without doing a check first. So obviously that is the case because we haven't actually stored anything within those variables. Now, if we press continue, we're going to continue to our next breakpoint as we can see, things have changed a little bit. Needed now stores 1284. Prox is storing 1, which is basically the Boolean version of true, or the integer version of the Boolean true, and prox array actually holds useful information. So we can actually see what looks like process identifiers here. Now, if we keep scrolling down, we're going to find something interesting. We're going to find eventually we get back to these 0 CCCCCs. And this is basically the end of our process identifiers. We can actually find the number of processes that are returned by this function fairly easily. And here's how we can do that. Now, needed is going to be the variable that holds the size in bytes of how much space we need within our process array to store all of process IDs. So what we can do is we can divide that by the size of an individual D word to get the number of processes that we actually have, the number of process identifiers technically that we actually have. So we can store that in unsigned int number prox is equal to needed divided by the size of an individual D word. Now, we're going to do a little bit of debugging information. Let me go ahead and remove these breakpoints here and here. And we're going to say if prox, then we're going to print out some debug information. We're going to print out first found processes. We're very excited about that, so it's all caps. And I'm going to go ahead and get rid of this before and after because those were just for debugging. So we've got found processes. Then we're going to print out /t for tab over to kind of keep things a little bit neat and clean. And we're going to say number of processes %d for a integer, and we're going to pass it in prox right there. And then we're going to do printf /t first PID, which is always going to be 0, which it has something to do with the Windows operating system that I can't remember just right off the top of my head, but basically your first process identifier returned by EnumProcesses is going to be a PID of 0. So first PID %d again, and we're going to pass in prox arr at 0. And do that, semicolon, and we are good. So, nothing just super interesting here. Oh, we forgot new lines, /n and /n. Let's run it again. We've got number of processes 320, and the first PID is 0. Exactly what we expected. Now let's move on to getting actually interesting information. Now, as we saw earlier with our kind of debugging session, our short debugging session, all we've got is PIDs. PIDs don't actually tell us what's running on the system. If we look over here at Process Explorer, we've got PIDs, we've got the name of the process here, which is basically just the executable that started the process, and tons of other information. We're not going to get to the tons of other information, but it would be useful to at least get the name of the process here. You know, that is the very bare minimum of what we kind of want to get here. So we're going to need 2 different API calls for that. Now, you could probably guess that we're going to use a for loop to loop through each individual PID within our array to get, the names of each of those individual processes. So let's go ahead and create that for loop. For int I equals 0. I is less than the count of the processes, or the number of the processes. I usually use cprox. And we're going to do I++. Now we are going to create a tchar variable, which is just another kind of string-like variable. Tchar, and it's going to be a pointer, proc name. And we're going to create it on the heap because we do need to pass the pointer, but we're not going to initialize that variable quite yet. So we're going to do new tchar of size max underscore path. Now, max underscore path is basically a variable that holds the maximum size that a path can be on your operating system. In this case, you can actually scroll over it and see that it's 260. So Windows, or at least my version of Windows, defines the maximum size that a path can be as being 260. So we're going to actually create our own function here in a second called getProcName, and we're going to pass in the individual PID. So procs are at I. And we're going to pass it the location of where we want the actual name of the process to be stored. So that is going to be proc name. All right, so obviously we haven't created that function yet, but let's go ahead and get to the prints afterwards. And we're going to kind of make a mess of this. We're going to call two different print functions, printf and tprintf. Our tprintf is going to be what we use specifically to print out tchar, variables. Printf doesn't handle them very well. You're going to have to do some type conversion, so I figured instead let's use the tprintf function. And that is why we included the tchar.h file. So printf, we're going to print out PID number %d and %d /t/t. Now this looks like a bunch of nonsense. I'll explain it here in a second. The first integer that we see here is going to be I. That is going to be the individual, like the actual index. So basically 0 through 300 and something. I can't remember what the exact thing was. And then we're going to print out the actual PID, which is going to be procs arr at I. And this right here, the tprintf, is going to print out, obviously our proc name variable, which is going to store the actual name of the process that, was being called. So tprintf is going to print out %s and /n. We're going to pass in proc name. Now we have to cast this as a text variable, not entirely sure why, but we're going to cast it right there, and we should be good to go to create our getProcName function. Now getProcName is going to be using two different API calls. getProcName, like I said, it's going to be a void variable. We're not super worried about returning anything because basically we're just going to be writing into an individual memory address. So what it's going to be passing in, it's going to be passing in a dword PID, and it's going to be passed in a pointer to a tchar ret. And ret is just, it stands for return, and PID stands for process identifier. Fairly easy stuff there. Now let's talk about handles. All a handle is a data structure that holds information about different objects on the system. Those objects can be processes, they can be modules, which we'll talk about later. They can be windows. A handle is just basically a general data structure that holds information about objects within the OS. That can be a bunch of different things. What we're going to create here is a generic handle. So it's going to be called handle h process, and we're going to use the OpenProcess function in the Windows API. OpenProcess, all it does is exactly what it says it does. It opens up a process's memory and can read, write, do all kinds of different things with it. We're going to use it for a very, very simple, kind of use case. All we're going to do is read information about that process. So one of the things that we're going to pass into this function, as we can see here in a second, is the permissions flags. All we really need to do here is read information about that function. In my RRE, or reverse engineering series, you can watch that one and see that I use the OpenProcess function to actually inject code into another process. We're not going to do anything complicated like that. All we're going to do is read information about it. So let's open up the MSDN article about OpenProcess. So the OpenProcess function, as we can see right here, you get a handle returned, a handle to the actual process itself, which, like I said, all it does is hold information about that process. We've got three different inputs to this. We've got DW desired access, B inherit handle, and DW process ID. The process identifier, obviously fairly self-explanatory. That's one of the kind of inputs to the function that we've created. The bInherit handle isn't something that we're super worried about. It's a Boolean variable that basically determines how the process is going to behave in the future. Since we're not doing anything complicated with this process, we're just going to pass false to this. It doesn't really matter. The DW desired access is going to use different process access rights flags to basically tell OpenProcess, hey, what are we going to be doing with this handle? If you open up the process access rights page right here, you can read more about it, but I'll give you the flags that we're actually going to use for this and explain them a little bit. So the flags that we need here are as follows. It is process query information, which is basically just telling OpenProcess, hey, we want to read information about this process, and we're going to OR that with process VM read, which is basically just saying we're going to be reading, from the memory of this process a little bit. We're going to pass in false for bInherit handle because we're not super worried about that, and we are going to pass in the PID. Now, if this isn't null, if this doesn't return a null handle basically, so if hProcess does not equal null, we're going to fairly quickly get to our next API call. First, we need to create two new variables. HModule, which is a handle to a module. I'll talk about what a module is here in a second. HMod, and a dword of CB needed. Now, the next function call is going to look very, very familiar. Basically, we're going to be using the exact same process of calling a functionally void API function to overwrite or to write into one of the items that we passed into it. So this HModule variable right here is eventually going to hold a handle to a module. Now, what is a module? All a module is a DLL or an executable that is run by another process. If we open up Process Explorer and we go to any individual process on the system, I'm using Discord right here. Like I said earlier, I've got a Discord server. Feel free to join it, and we can talk about all kinds of really cool Windows API research and fun stuff like that. But if we look at this lower pane, we can see all of the different modules that Discord is using. ADV API 32 is the Advanced Windows 32 base API. It uses, it's a lot of the API functions that we're using right now can be found in that API DLL file as well. We've got bcrypt, which is cryptographic primitives, all kinds of fun stuff in there. And, basically all of these are the different DLLs mostly and executables that are run by an individual process. Now, why are we doing this? Because we are interested in the very first module that was run by this process or that was imported by this process. Now, what would that be? The first module that is used by a process is going to be the executable that actually ran that process. You'll find in this list somewhere is discord.exe. I'm sure it's somewhere. Or maybe it's not. I don't know. Yeah, you can find it right here. So we're interested in finding that module. Now, this looks like it might be very, very difficult because we've got this huge list of imported modules. So how are we going to find, the needle in the haystack, the one module that we're actually interested in? Well, the Windows API does us a solid by making that the very, very first item that is returned from EnumProcessModules. That is going to be the very next thing, or the very next API call that we run. So if, we're going to wrap it in an if statement, EnumProcessModules, and we will eventually get to what we're going to do within these brackets, but for right now, let's look up what EnumProcessModules does and how to call it. As usual, we're going to stick with MSDN. So it says that EnumProcessModules function is found within the psapi.h, which is one of the headers that we imported, and this is how you call it. Now it says up here, retrieves a handle for each module in the specified process. Then it tells us, what we can do for 64-bit applications and, different things like that. So we've got EnumProcessModules, and it takes as input the handle to a process, and it takes as an output input variable, which is the exact same thing that we did earlier with the EnumProcesses function. Basically, it's going to take a pointer that it's going to then store a list of modules in. Then it's going to take in a size, which is CB, basically the count of the bytes that it's needed, and then it's going to return the amount of bytes that it actually needs. Now, here's the trick. Since the very first item that is returned by EnumProcessModules is the module that we're interested in, it is the executable file that actually ran this process or that started this process, we don't need to pass it in a list. If we can look back at our code here, I didn't create a list of HMODs, I created one individual HMOD. So all we actually need to do is pass in that one individual HMOD and the size of that one individual HMOD, and it's going to tell EnumProcessModules, hey, we're only interested in the first item within the array that you're going to return. So we're going to pass it in hprocess. We're going to pass it in the pointer to the HMOD, so HMOD, actually I believe it's and HMOD. We're going to pass it in the CB needed, and we're going to store, oh wait, nope, that's wrong. We're going to pass it in the size of HMOD, MOD, and then we're going to pass in CB, or the location of CB needed. So that's going to ensure that it's actually going to store that in the location. We're not going to pass the value, we're going to pass the location. All right, so that is going to return the very first module that was used within a process, which is going to be the executable that started that process. And it is going to store a handle to that module within HMOD. We're not going to worry about CB needed because we're not creating an array. That's mainly for checking to see if you need to allocate more space or more memory for an array than what you're passing in as default. Now, right after that call, we're going to use another API call. This is going to be the last one, I promise, and it's actually the simplest one as well. So GetModuleBaseName. Literally all this does is it takes a module, a handle to a module, and it is going to return in a tcar variable the actual base name or the name of the executable that ran that module or that is associated with that module. And it takes a couple of things as input. It takes the handle to the process, hprocess. It takes the handle to the module. It takes a location where it's going to store that information as a tcar variable. So we're going to give it ret. And it takes a size. So max underscore path divided by the size of a tchar. So that's going to give the actual size of that, in bytes, the max size in bytes instead of, in characters. And that's going to give us what we need. And it's going to store it within this ret variable, which, as you can see, is the way we passed it in was by location. So it's just going to store that within the location that we passed it right here within procname. All right. So to recap, this is what is going on here. Our main function enumerates all of the process identifiers and stores them in an array. It then calculates how many processes are actually running on our system at any given time, and it's going to print out a little bit of debug information here. After that, it's going to loop through every single process identifier and pass it to getProcName, along with a location where getProcName is going to store the name of the executable that actually ran that process. If we go to getProcName, the way it does that is it opens a handle to the process with the kind of permissions of, we just want to read about this. We're not trying to write anything. We're not trying to inject anything. We just want to read about it. If we hop into that process right here, we're going to open up a handle to a module. That module is going to be the very first module that actually ran the process that we're dealing with right here. And that is returned by EnumProcessModules. That handle is then passed to GetModuleBaseName, which is going to find the name of the executable that is associated with that module. That's it. Super easy stuff. Now we are ready to run. Let's go ahead and run this. And as you can see, we don't get exactly what we expected. We get interesting information. As we can see, we've got discord.exe here. We've got processexplorer.exe. All of these are things that we know runs on the system, but we've got a lot of question marks, like literal question marks here. I did a little bit of debugging on this, trying to figure out exactly why we were getting all of these question marks. It's kind of strange. What I found was I've got a couple of hypotheses. Some of these things are associated with administrative kind of functionality. So if you looked at a couple of these process identifiers within Process Explorer, you'd see that some of these are associated with, some Windows administrative functions like service host and runtime broker and con host and things like that. So if we look at PID 34700, let's see if we can find it. Yeah, it's going to be difficult to find, huh? So we look at 34700. I need to be way further down. 34700, we obviously get some question marks there. That is an administrative function. Service host, we'd probably find the exact same thing. 34692. Actually can't even see that in here, so it may be missing. So yeah, if we went through this list exhaustively, we would find pretty quickly that a lot of these are associated with administrative functions that we very well may not even have the rights, the access rights to read from. You might be able to run this in administrative mode and get that information a little bit easier. But as of right now, we don't have the permissions to actually read from at least some of these processes. And that means that we're getting these question marks that I'm sure if we ran through this in the debugger, we would, understand a little bit easier. But for the most part, you can at least view information about the majority of the things that are running on your system. Maybe not even the majority. A lot of the things that are running on your system, you can see information about. Thank you so much for watching this video. The recording went on a lot longer than I expected, but we got there eventually, and we got something running. We're going to perfect this in later episodes. We're going to figure out some of these bugs with the question marks, and we're going to explain exactly why all of that works. But I wanted to take the time to at least get something relatively educational out. Thank you so much. I will see you in the Discord and see you in the comments. Take it easy.